Mark P. Otten back with you.
Okay, so this is your chi-square test lesson for Psych 320. Part 1 is going to be the SPSS, and Part 2 is going to be the by hand, or actually more like in Excel, version of doing a chi-square. So the first part here, I want to show you one trick in SPSS that will allow you, if you haven't seen this before, which I'm sure most of you have not, which will allow you to label your variables appropriately. So this is an example where this is real data from a past 320 class, and we've got gender and dog ownership as our two variables. So we're going to start with gender, analyze that by itself, and then we're going to add in dog ownership as the other variable of interest. And we can make some hypotheses. My gender hypothesis will be that there were more females in the class than males in this case, knowing that it was a psychology class. And then the other hypothesis is that in the relationship between gender and dog ownership. So I'm going to hypothesize that males were more likely to own dogs than females in the class. So I don't know why I picked males there, but maybe the old slogan, "A dog is a man's best friend," is my background research that has fueled this hypothesis. Well, I don't know. We'll see. Anyway, as far as labeling goes, I'm in data view here. I entered in just 1s for females and 2s for males, and then I entered in 1 for dog owner and 2 for non-dog owner. So in data view, if you scroll down, you see eventually there's some 2s there in each column in addition to 1s. What does it all mean? Well, to keep it straight, you go back to variable view and you click on values here. So what you do is you highlight this cell. When you highlight that cell under values in the gender row, you see a box pop up that's like a pop-up window that will pop like that when you click on the little box there. And I'm going to say the value 1 is female and click add, and then value 2 is male. And what this will do is when you go back to your data, the 1s will be clarified as females and the 2s will be clarified as males. So you click OK. You do the same thing for dog ownership here. If you highlight this cell, click on the square within the rectangle there in that cell. Let me do that one more time. There's a rectangle there on the right side of the cell for values, column, dog, row. Click on that. Value labels will pop up here. You're going to go 1 dog owner add and 2 non-dog owner, something like that. Or you just say dog, no dog if you want. And what this will do is clarify who the dog owners are and who are not, 1 being dog owner and 2 not. So click OK, go back to data view, and they're labeled like so. Now if you didn't get them automatically labeled immediately like that, it's because you needed to click this button up here in the toolbar. It's labeled like a with a 1, and there's like an arrow, 2 arrows in between or something like that. That means you're just changing from letters to numbers and vice versa by clicking on that button. So if you click on it, it takes you back to numbers. Click on it again, it takes you back to letters. The A1 button always makes me think of steak sauce for some reason. But anyway, so now if we have the letters selected there, the labels are selected, that is, and then we can go down. If we make this wider, the labels will be there for you. Okay, so with the setup for a chi-square here, the labels are actually optional, but I always recommend them because it helps you keep the data straight. In order to evaluate our hypotheses, then we're going to go into the gender row. We're going to figure out how many females are there and how many males are there, and then compare that to the null hypothesis that there is no gender difference. So what we're doing here, I mean, you can just scroll down. Looks like 61 lines of female and a total of 90 people. So if you go 90 minus 61, that's 29 males, right? So you can just count. You can be like, well, okay, there's more females than males. But really what we're doing with the chi-square is we're counting 61 compared to 29, and we're comparing that to the scenario under which there's no gender difference. So imagine there's no gender difference in the class. If we have 90 people, how many females would there be? Well, there would be half. It would be 45 females and 45 males. In the scenario, we have 90 people and no gender difference, right? here we have 61 and 29 females versus males. So there is a suggestion that there are more females than males, but the missing piece then is to test that hypothesis and determine if 61 and 29 is significantly different than the scenario in which you have 45 and 45. So we'll see that play out in Excel in the math in a little bit later in this video. But meanwhile, we're going to ignore the dog ownership variable temporarily. We're going to go to Analyze, and we're going to go to Non-Parametric Tests, Legacy Dialogues, Chi-Square. Whew, that's a mouthful. I had to take a sip of my coffee to get past that one. All right, so non-parametric test, it's like a long string of, it's a different location too than the other chi-square that we're doing in a minute here. It's just a long way to go to get to a relatively simple test. This is the chi-square test for one variable. We're going to get to the chi-square test for two variables in a minute. But for one variable, just gender here, we're going to go to chi-square, and we're going to pop gender over to the right under test variable. Like I said, we're ignoring dog ownership for the moment, and we're going to click through. So click OK. That's all you have to do is move gender over. And you've got two boxes here. The second box is, well, the first one confirms what we already were talking about there, the totals, 61 compared to 29, females compared to males. The expected N is the 45 scenario that I was just talking about. And when we get down here to the bottom box, we're going to get a chi-square of 11.38 and a p-value of 0.001. So what does this mean? Well, the p-value, first of all, is, I'm calling asimp sig. The p-value asimp is asymptotic, and sig is significant. Again, a fancy label to denote something very simple or very well known, which is your p-value. So the p-value 0.001 is less than our conventional criteria of 0.05. Thus, we can reject the null hypothesis, and this is going to be the rule that applies to all tests that we run. That is that we can reject our null hypothesis if the p-value is less than 0.05. The chi-square value 11.378 there, that is your test statistic, and I'm going to come back to that in the Excel part here, because we're going to actually calculate that value, and then we're going to compare that value to a critical value to confirm what we already know, which is that the p-value is less than 0.05, and thus we should reject our null hypothesis. In this case, if we're rejecting our null hypothesis, we are saying that what are we rejecting? We're rejecting the scenario under which there is no gender difference, and thus we are concluding that there is a significant gender difference. And in this case, looking back at the observed values, we can deduce that there are more females than males in the class, significantly so. Okay, so that was our first chi-square. Now we're going to go back to our second chi-square. We're going to add in the dog ownership variable, and this is going to be our second variable to then make a more in-depth hypothesis. So suppose we already know, maybe we don't know, but we haven't made any, we're not editing that gender conclusion that we just made. We're concluding confidently there's a gender effect, there are more females than males in the class. But now we're saying, okay, now that's maybe interesting, but it's not the whole story. The whole story that we're trying to tell here is that males are more likely to be dog owners than females. And that's sort of regardless of how many males there are in the class. So you can imagine there's only 29 males in the class. That's fewer students, right? Fewer than the females. But of those 29, maybe 99% of those people, those students, are going to own dogs. That could be our hypothesis. And the same would not then be true for females. For females, maybe only 50%, maybe only 20% of the class is a dog owner. So that would be our hypothesis before collecting any data. Then we collect our data and we see, as you can see on the screen here, there are a bunch of male non-dog owners. So by just collecting the data, we can kind of see that, hey, that might not be the case. There are so many male non-dog owners here that maybe our hypothesis will not be supported. But we don't really know until we run the numbers. So I'm going to go back to Analyze. We're going to go to a different place this time. We're going to go to, I don't know why, Analyze Descriptive Statistics, cross tabs. And I'm going to put gender over to row and dog over to column. What that does is it sets up a table for you in the output. It doesn't actually matter which you choose. I'm just putting gender into rows and dog into columns arbitrarily. You could switch those and you'd still be okay. But you're not okay to click OK yet. You have to. The most important step here remains. You're going to go to Statistics and select chi-square, and that's actually going to give you your two-variable chi-square result. So click Continue and click OK now, and this will give you your output again. So now you've got a little bit more output, but some also that's unnecessary in this case. The first thing to look at here is our table that I alluded to. We have our breakdowns of how many females, how many males, first of all, are in the class. You see the 61 and 29 there on the side. Then you see the 47 and 43 on the bottom. That means that 47 people in the class own dogs, 43 don't. So it's a pretty even split. And then among the females, 33 own dogs, 28 don't. And then among the males, 14 own dogs and 15 don't. So you can already see that that there are not more male dog owners, whether you're looking at 14 compared to 33 there, or whether you're looking at the percentage. More accurately here, you're looking at the percentage. 14 out of 29 males, or slightly less than half of males, own dogs. 33 out of 61, slightly more than half of females own dogs. So if we had hypothesized that males were more likely to own dogs, we are thoroughly wrong before we even run our test by just counting our numbers there. But we run the test anyway, and this top line of this chi-square test box is your chi-square test. There are some corrections and other statistics there that you don't really need to pay attention to for the purposes of this example. What you need is that top line. The 0.267 value is your test statistic for the chi-square test, which again we'll come back to in a minute, along with the degrees of freedom, which will matter also in a minute. And then the most important thing for now, the p-value there, 0.605, that's in the asymptotic significance two-sided column. Very fancy label, just call it the p-value, you'll be okay. The 0.605 value is greater than 0.05, right? Your conventional criteria there for rejecting a null hypothesis. So this is the opposite of the last one. The last one, the p-value was less than 0.05. We rejected the null hypothesis. Here, the p-value is greater than 0.05, so we're not rejecting the null hypothesis. And what we're doing is we're concluding that there is no difference in males and females regarding dog ownership, or males are not more likely to own dogs in this case than females, nor are females more likely to own dogs compared to males. There's just no gender difference there in how likely someone is to own a dog. Okay, so this is your one variable chi-square example as seen in Excel. So I'm going to go ahead and fill in our observed values here. This is 61 and 29. This was our count of females and males from the past 320 class. And when we ran this through SPSS, we already rejected our null hypothesis and because the p-value was less than 0.05. So this is kind of redundant, but what we're doing here is we're showing you where the numbers came from in terms of getting that test statistic anyway that you saw in the output. So that test statistic came from some comparisons of observed values to expected values. So what are these expected values? Well, I told you they were 45 and 45. Where did that come from? Well, we had 90 people, so the total here, if we want to call this total, 90 people in our total in our class, and so then that can be carried across here. So the total dictates the expected values. In this case, we have two categories, female and male. So half the class is female and half the class is male if there is no gender difference. Now the expected values represent the null hypothesis in the sense that the number of females under the null hypothesis is no different than the number of males. And so then technically you get that 45 by taking 90, which is your total number of people, and dividing by the number of categories. In this case, the number of categories is 2, so 90 divided by 2 is 45. I just did 45 and 45 because that was half of 90, which is the same thing implying that there is no gender difference. So what we're doing here with the chi-square, again, is comparing our observed values to our expected values, or we're trying to see if our pattern of 61 females and 29 males is in fact different than the scenario under which there is no gender difference. So what that means is we go over here, we have our chi-square test statistic formula, which is observed value, which is the O minus expected value squared, so we're squaring it. Looks like a little bit like a standard deviation in that sense. And then you're dividing by the expected value, which just sort of puts things back on a scale, or puts the statistic relative to the expected value, in this case 45 in each case. So we're going to take our Excel formula, the cell there, and type in a formula to the cell in Excel. And we're going to start it with an equals and a parentheses. Looks like a frown, but that's not, this is actually very happy. Maybe I should change it to this. No, that's not true. I'm going to change it to that. Okay. So we're going to go 61 minus 45. That's observed minus expected. We're going to square it with the caret, or the capital 6 on your keyboard, caret 2, and then we're going to divide by expected, which is 45. And we're going to get 5.69. Then we're going to do the same thing for the next one, equals parentheses 29 minus 45. Again, observed minus expected squared divided by 45 again. And it's going to be the same number. That happens that way when you have two categories. When you have three categories, that number might look a little different the second time. But here, if you have two categories, you know you did it right, actually, if those two values are equal to each other. And then for the test statistic, you're just going to take the sum of those two values. So equals SUM gives you sum, parentheses, you can highlight those two values, end the parentheses there, and you see what the formula looks like. You could also just do equals 5.6888 plus 5.6888. It's going to give you the same thing. And here it's going to give you 11.378, which was your test statistic that we saw in SPSS. Now, what do we do with that? Well, this goes back to your hypothesis testing golden rule. If the p-value is less than 0.05, you reject the null hypothesis. If the test statistic is greater than the critical value, then you reject the null hypothesis. And then by extension, if the p-value is less than 0.05, the test statistic will be greater than the critical value. So what do we need here? What's missing? That's the critical value. So I'm going to go to the chi-square critical value chart. This is posted on your Canvas page. And for this, you need the degrees of freedom. You can steal those, in this case, from SPSS. If you look back at your SPSS output, your degrees of freedom was 1. Or you can calculate it. In this case, degrees of freedom is just number of categories minus 1. So the number of categories was 2, male and female. So number of categories minus 1 gives you 1. And your critical value then is under the 0.05 for p-value column, and you're going to go with 3.84 here for your critical value. So again, degrees of freedom 1, that is number of categories minus 1, in this case 2 minus 1, and the p-value column there that we're worried about is 0.05. So 3.84, your critical value, less than your test statistic, 11.38. Thus, as expected, we reject our null hypothesis. Okay, so now we're ready for our two-variable chi-square. So we're splitting up our observed and expected values here into tables. This first observed value table is your breakdown of females and males in the class and dog ownership versus no dog ownership. So this was also printed in your SPSS output to confirm the counts for the different categories. So for example, 33 females owned a dog, 28 females did not own a dog. The total female count there 61, and so on. If you go down the first column there, 33 females owned a dog, 14 males owned a dog, so 47 people in total owned a dog, and so on. So that's where you get those column and row totals. Total number of people in all was 90 students. So then you're going to go to your expected values for the same kind of comparison as before. We're trying to figure out if this scenario, these observed values here that we see are suggest a different pattern than what would be expected if there were no gender differences between dog ownership. That is, the expected value table should reflect that males are just as likely to own dogs as females. And if that expected value chart is very different then your observed value, suppose we had like, out of 61 females, suppose we had 59 dog owners and 2 that were not, then we would know that there's a difference, right? There's a clear trend going on. Here we see 33 females compared to 28 in terms of dog owners versus not. That's slightly more females with dogs compared to not. For males, 14 dog owners, 15 non-dog owners. So there's slightly less than half of the 29 males have dogs. So we're really not seeing any like patterns that jump out at us in terms of possible relationship between gender and dog ownership. So we're really not expecting much here. But we're going to make the calculations and run the test just to double check that. So, and that's the fun part, right? All right, so for this expected value, it's a little bit, it requires a little bit of multiplication and division. So we're going to go equals, I'm going to take 61, which is my row total, and multiply it by 47, which is my column total. I think I made too many parentheses, more than necessary there. So that's okay. More parentheses is okay. All right, divide by the total, 90. So what that does is, for female dog ownership, that category, you're taking your row total, which is your number of females total, multiplying that by 47, which is your total number of dog owners, and then dividing by 90, which is your total number of students in the class. That's going to give you an expected value of 31.9 females that own dogs. I don't know how we could have 31.9 people in the class, but anyway. Next one, males will be, if you see the pattern here emerge, then that's a good sign. So 29 is your row total, 47 is your column total. I'm not using the parentheses this time because I kind of overused them before. If you just go in order there, 29 is multiplied by 47, divided by the total of 90 gives you 15.1. Then we go up here, 61 is still your row total for female non-dog owners, but now you got to multiply by 43 because that's your column total, divide again by 90. 90 is consistent throughout. And then lastly, you've got 29 here for your row total, that is number of males in the class multiplied by 43, number of non-dog owners in the class, and divide by 90, the total again. So you got your expected values there. You can start to interpret if you like, but we're going to not do that. We're going to just take it straight to the formula here. So the formula is the same as before again. We've got observed minus expected, O minus E squared, divided by expected. We're going to be doing this 4 times. In the single variable example, we did it only twice. So here we're going to take our observed value for female dog owners, that's 33, subtract the expected value. You can click on this directly if you want to keep all the decimals. I'm going to do that, 31.8555 and so on. So by clicking on that cell, it says B9 in the formula there, but it's going to give me the value that's in that cell. So 33 minus B9, or 31.86, square that after the parentheses and divide by the expected value, which is again this B9 value. So I'm going to click on it a second time for the bottom part of the fraction. And you're going to get 0.04, which is a very small value. Again, we'll interpret in a minute. So meanwhile, we're going to do this for the other 3 cells as well. So the observed value for males was 14 minus the expected value. This is male dog owners, that is, minus 15.14. Square that and divide by 15.14 again. You have 0.09. For female non-dog owners, you're going to get observed value of 28, a expected value of 29.14. Square that and divide by 29.14. And again, these correspond to each other in the observed and expected tables. So that 28 there is in the top right for female non-dog owners. In the observed box at the top there, the expected value is also in the top right for female non-dog owners in the expected value table. So this one's going to give us 0.04, and then finally for, are you bored yet? No, this should be fun. For male non-dog owners, 15, your expected value minus 13.86, your observed value minus your expected value squared, divided by the expected value, which again is 13.86, or the value in C10. And there's your value for male non-dog owners. Okay, so all you got to do from here, you've done most of the work now. all you got to do is take your 4 values here in this observed minus expected squared divided by expected table and sum those up. So I'm just going to go equals. I'm going to click on each one with a plus in between. And this sum is going to be your test statistic for the 2-variable chi-square. So again, you take those, the bulk of the work I think is to get those expected values, then subtract them from the observed values in the formula there. You're going to get 4 values in this case because we have 2 categories for gender and 2 categories for dog ownership. And then once you've done that, you just need to add up the 4 values. And you're going to get your test statistic of 0.267, which should match your test statistic that you got in SPSS. Okay, so once again, we have our test statistic, and we're going to compare it to a critical value. Now this again is redundant. We found that in the SPSS earlier that the p-value was greater than 0.05, thus we knew not to reject our null hypothesis, and thus we knew that there was no relationship here between gender and dog ownership, no significant one. So this is again redundant, but it showed you where the numbers come from, and the numbers send all into that test statistic value that we just calculated, and that test statistic value is compared to the critical value by this table here again. So again, we're going to end up with this 3.84 value. The degrees of freedom is still 1. The degrees of freedom, though, when you have 2 variables like this, and this is shown in your roadmap, hypothesis testing roadmap, the degrees of freedom is number of categories minus 1 times number of categories minus 1, because we have 2 different variables here, right? The first variable is gender, 2 categories, male and female. The second variable was dog ownership, 2 categories, either you're a dog owner or you're not. So 2 minus 1 for gender gets multiplied by 2 minus 1 for dog ownership. The result is, of course, 1 times 1, so you end up with 1 still. So the degrees of freedom is the same as it was before, but there's a little bit more that goes into it than there was before, because you have those two variables, each with 2 categories. So again, 2 minus 1 times 2 minus 1 gives you 1 times 1, or 1. And we're still using 0.05 for our criteria, because that's what people do. And so then we get 3.84 for our critical value. In this case, however, the decision is reversed from before, right? The what was it? I lost it. 3.84, thank you, is now greater than your test statistic, or that is, your test statistic is less than your critical value, and thus you do not reject the null hypothesis, whereas before you did. So this again matches your SPSS output. The p-value was 0.605, which was greater than 0.05, so we knew not to reject this null hypothesis either.